Hi guys, welcome to the next section, using convolutional neural networks for predictive analytics. Now, we move on to the first video of this section that deals with CNNs and the drawbacks of regular DNNs. In predictive modeling, CNNs are a type of feed-forward neural network in which the connectivity pattern between its neurons is based on the animal visual cortex. In the last few years, CNNs have managed to achieve and demonstrate outstanding performance on some complex visual tasks such as biomedical imaging, image search, self-driving cars, automatic image or video classification systems, and more. Moreover, CNNs are not restricted to visual perception. They are also successful at other tasks such as voice recognition and NLP. Why not simply use a regular deep neural network with fully connected layers for image recognition tasks? The thing is that although regular DNNs work fine for small images, it breaks down for larger images because of the huge number of parameters it requires. CNNs solve this problem using partially connected layers. Because connective layers are only partially connected. Because consecutive layers are only partially connected. Because it heavily reuses its weights, a CNN has far fewer parameters than a fully connected DNN, which makes it much faster to train, reduces the risks of overfitting, and requires much less training data. Moreover, when a CNN has learned a kernel that can detect a particular feature, it can detect that feature anywhere on the image. In contrast, when a DNN learns a feature in one location, it can detect it only in that particular location. Since images typically have very repetitive features, CNNs are able to generalize much better than DNNs for image processing tasks, such as classification, using fewer training examples. For example, in the following figure 1, on the left, you can see a regular 3-layer neural network. On the right, a ConvNet arranges its neurons in 3 dimensions as visualized in one of the layers. Every layer of a ConvNet transforms the 3D input volume to a 3D output volume of neuron activations. The red input layer holds the image, so its width and height would be the dimensions of the image, and the depth would be 3. Now, let's move to CNN architecture. In CNN networks, the connection scheme that defines the convolutional layer is significantly different. The convolutional layer is the main type of layer in CNN, where each neuron is connected to a certain region of the input area called the receptive field. In a typical CNN architecture, a few convolutional layers are connected in a cascade style, where each layer is followed by a rectified linear unit layer, then a pooling layer, then a few more convolutional layers, then another pooling layer, and so on. The output from each convolution layer is a set of objects called feature maps that are generated by a single kernel filter. Then, the feature maps can be used to define a new input to the next layer. Each neuron in a CNN network produces an output followed by an activation threshold, which is proportional to the input and not bound. Next, we will see convolutional operations. A convolution is a mathematical operation that slides one function over another and measures the integral of their pointwise multiplication. It has deep connections with the Fourier transform and the Laplace transform, and is heavily used in signal processing. Convolutional layers actually use cross-correlations, which are very similar to convolutions. Thus, the most important building block of a CNN is the convolutional layer. Neurons in the first convolutional layer are not connected to every single pixel in the input image, but only to pixels in their receptive fields. In turn, each neuron in the second convolutional layer is connected only to neurons located within a small rectangle in the first layer. This architecture allows the network to concentrate on low-level features in the first hidden layer, then assemble them into higher-level features in the next hidden layer, and so on. This hierarchical structure is common in real-world images, which is one of the reasons why CNNs work so well for image recognition. Now, let's apply convolution operations in TensorFlow. TensorFlow provides a variety of methods for convolution. The conical form is applied by the conv2d operation. Let's have a look at the usage of this operation. The first parameter used is input. This is the original tensor to which the operation will be applied. It has a definite format of 4 dimensions, and the default dimension order is shown below. The next parameter is filter. This is a tensor representing a kernel or filter. It has a very generic method. Another parameter is strides. This is a list of 4 int tensor data types which indicate the sliding windows for each dimension. Next, we have padding. This can be same or valid. Same will try to conserve the initial tensor dimension, but valid will allow it to grow in case the output size and padding are computed. The next parameter use CUDNN or GPU. This indicates whether or not to use the CUDA GPU CNN library to accelerate calculations. The last parameter is data format. This specifies the order in which data is organized. Further is an example of a convolutional layer, which concatenates a convolution, adds a bias parameter sum, and finally returns the activation function we have chosen for the whole layer. Here, x is the 4D tensor input.